Good day, everyone. Welcome to ME 160. And now we begin with 2 degrees of freedom. So, our goal for this lecture is first of all, we want to model 2 degrees of freedom systems in a vibrational sense. And next, we want to derive the equations of motion for these systems. And then, so okay, we have our equations of motion. We can now determine the response of our systems. Now, when we have 2 or more degrees of freedom, we typically look at our systems and see if whether we can gain a bit of accuracy in exchange for more complexity. So, for example, let's say we have a bicycle. So, when a bicycle hits a speed bump or encounters a pothole, you would know that the front wheel will bounce first before the rear wheel, at least if you're moving forward. So, the fact that these wheels will encounter the disturbance at different times means that you cannot just simply model this bike as a single degree of freedom system. Otherwise, the wheels will bounce at the same time when the speed bump uh, is encountered. So, how do we model, for example, this bike as a 2 degree of freedom system? So, one way that we could do it is we can assume that this entire body is rigid and it is sitting on 2 springs. So, what are those 2 springs? That would be the rubber wheels. So, if we take this model, then we can assume that this bicycle is some rigid body and those wheels are acting vertically. So, each wheel will have its own separate vertical coordinates. So, sir, what happened to the wheels? Why are they planted to the ground? That is because, relative to this body, at least if it's riding on level ground, it's as if the body itself is still. And if the body encounters some disturbance on the ground, then the ground will just shake, and that shaking will be passed on to the rigid body. So another way to model this is to assume that the entire body is under general plane motion. So instead of 2 separate vertical coordinates, you have one coordinate translating on the centroid of the body and one angular coordinate that is rotating about the center of rotation of the body. So these are 2 methods of modeling this bicycle in 2 degrees of freedom. So you might ask, okay, so sir, which one is the preferred one? Now, when we select models, it is entirely up to the circumstance. Maybe it is more apt for one application to model the bike this way as a seesaw of sorts, or as a body that is undergoing general plane motion. So that entirely depends on the application. So speaking of which, there is another application for 2 degrees of freedom. So like for example, we have what we call a tune mass damper. So what does this tune mass damper do? So this is a device that is installed on buildings, on high-rise structures, and their function is to absorb the shaking from any earthquake-induced vibration on the ground. So as you can see here, you have a quote unquote pretend building that doesn't have a TMD or tune mass damper versus one that has a free moving tune mass damper. And you can see here the fact that you have a free moving tune mass damper connected to your building means that the behavior of the building itself is changed. Hence, you cannot model a TMD building as a single degree of freedom system. So the tune mass damper, we will return to this. This is actually quite a bit of a doozy, but this 2 degrees of freedom discussion will be set up for that. Another system that cannot be modeled in single degree of freedom but only in 2 degrees of freedom is the double pendulum. So the double pendulum is actually quite well known in mathematics for being an entirely chaotic mess. So if you see here, this is an animation of a double pendulum that is not undergoing a small angular displacement. And the problem here is that there currently is no analytical solution for the behavior of a double pendulum. So you might ask, okay, so why does this animation exist? How did the physics engine come up with this kind of simulated behavior? So this kind of behavior was developed numerically. So when we say numerically, it was developed using iterations. It has a starting point, and then the iterative or the numerical methods for solving this kind of like extrapolated the behavior from there. So if you can solve for the analytical response of a double pendulum, then I think you deserve $1 million. I am not sure if it is being offered, but if you do solve for an analytical solution for this, you might get a lot of money from a lot of people. So right, that is 2 degrees of freedom. Those are 2 degree of freedom examples. Now, when it comes to single degree of freedom, typically we only have a single natural frequency. And because there's only one body that is essentially being vibrated, it only vibrates in one pattern. However, when we have 2 degrees of freedom, we actually have now two natural frequencies. And the thing about it is that if you have two natural frequencies for two sort of independently moving bodies, your vibrational pattern is no longer limited to just this. For example, okay, so we have 2 degrees of freedom, we have two natural frequencies. One natural frequency could make the system move this way, and the other natural frequency could make it move this way. So these are two different vibrational patterns that are assigned or triggered by two different natural frequencies. We call these patterns mode shapes. So when you think of mode shape, it's just the pattern of the vibration. And again, these patterns are connected or triggered by a particular natural frequency. So given this, okay, so we have two modes, two mode shapes for 2 degrees of freedom. Now, when we look at the response of these 2 degrees of freedom systems when it comes to disturbances, most often times the disturbance will be a combination or a superposition of these two modes. Now, these mode shapes are actually quite important. One of their applications is in determining which part will be stressed during a particular kind of operation. So, for example, if you have a satellite attachment, it is important to determine the natural frequencies and the associated modes of vibration of each of these frequencies. So if you look at these animations, they might look funky, but these are exaggerated vibrations. The vibrations might be smaller. However, the stress that the components undergo when they are exposed to this particular natural frequency could be quite catastrophic for their parts. So that is why it is best to try to anticipate or predict any um, any vibrational caused dynamic loading that will make all of these parts fail. So that is the importance of mode shapes. Now let's go on to solving for properties of a 2 degrees of freedom system. So for 2 degrees of freedom, we will maintain our course with analytical solving. So there will be no numerical solving in this lecture. So our task here would be to first find the frequency that is associated with each mode shape. So again, we're going to find the frequencies first, then find the mode shape that is associated with them. Next, okay, so we have our frequencies, we have our mode shapes. Let's get some mathematical properties that are associated with the frequency and the mode shape itself. And to begin, we start with a very symmetric looking system. So we have two masses here, mass 1, mass 2, and they are sort of supported by three springs. So we have K1, K2, and K3. Now, when it comes to 2 degrees of freedom systems, each mass in the system is sort of free to move on its own. So it is best to assign a separate x for each of these masses. So x1 for mass 1, x2 for mass 2. So in order to model this mathematically, what we do is we look at the equation of motion per mass. So let's start with mass 1. So for mass 1, this is kind of the same as with single degrees of freedom systems. The mass times acceleration of the body is equal to the forces that are acting on them. So here we have our mass 1, and what are the forces that are acting on this mass? So you have a spring force here from K1, and you have a spring force here in K2. Our equation then would look something like this. Wait, hold on. Well, what happened to the spring force? Why is it negative K2 x1 minus x2? So if we look at K2, we see that K2 is actually being influenced by the movement of the two masses. So here we have mass 1 associated with x1, and then here we have x2. So why is it in a difference? Why is it not in a sum? So think of it this way. If x1 moves in the positive direction, so to the right, the spring will be compressed, so it will store energy. If x2 moves in the positive direction, the spring will loosen. It will lose potential energy. So x1 and x2 are kind of acting against each other. So if x1 moves, it produces a restoring force in this direction. But if x2 moves in the positive direction, it steals some of that force that x1 is supposedly applying. Hence, you have a difference here. Negative k2 times the difference of x1 minus x2. If you examine mass 2, you will get a reverse of this difference. So x2 is now in the positive sense, while x1 is now acting against the force of the x2. So all right, we now have two free body diagrams. We now have two equations of motions, and what you notice here is that we group them according to their x. So you have x dot 1 here. We group the x1 terms. We group the x2. Same for this other side. Now we can combine these into a single equation by using the matrix form. So how do we go about it? I think you can figure it out using reverse matrix multiplication, but we will end up with this kind of solution. So how do you, okay, so we have our matrix equation. How do we go back to one of these equations? Like for example, we want to go back to equation 1. So to go back to equation 1, we just multiply this row with this column. So m1 times x double dot 1. 0 times x double dot 2, so it doesn't exist there. Next, we do the same for the second matrix. So x1 plus x2, k1 plus k2 times x1, so that is this one, minus k2 times x2. So here it is, and 0. So that is inverse matrix multiplication. So this matrix equation has a lot of parts. We have our mass matrix here. We have our stiffness matrix here. And of course, we have our displacement and acceleration vectors. Now, x1 and x2, they are still defined by the usual forms, but for now, we will use the complex exponential form, which is just the amplitude times the e raised to j omega nt plus phi form. So, all right, given this, so x1 and x2 actually form this particular matrix we call the displacement vector. So, this contains the displacements of all of the coordinates in the system. And likewise, we can name this one as the acceleration vector. Now, this might be a little too clunky to write repeatedly, so we can write this in short form. We can write them as this. So, M is just enclosed by square brackets, essentially, and K as well. And our vectors are donated by arrowheads in their as their hat, in a sense. Now, pay attention. This one is different from just plain zero. So when you see a zero in close brackets, that usually means it's a zero vector. So right, can we simplify this further? Of course. So if you recall from the single degree of freedom free response, x double dot is a multiple of x. So there's a reminder of this. So any x double dot of t is actually negative omega n squared x of t. So we can substitute this relationship into the m term, the mass term. And if you do so, you can actually combine these two separate matrices into one. So here they are. They are now combined as a single matrix, multiplied to our vector, and then it equates to a zero vector. We call this entire thing as our characteristic equation. And this matrix itself, this might be a familiar term for you. This is called the impedance matrix. So this is the impedance matrix. So okay, so we now have our characteristic equation. Let's find now our natural frequencies. So to find our natural frequencies, we have to solve for the natural frequencies that make this entire equation true. So as with before, we have two steps, or rather two approaches that can lead to the correct answer. The first one is to equate the entire vector to zero, but that is actually quite a useless solution, so we skip that. Instead, we look at our impedance matrix. If we get the determinant of this impedance matrix and we equate this to zero, whatever omega n makes that possible or makes this equation true is a natural frequency. So from this point on, we're going to simplify things. We're going to assume that all masses and all stiffness are equal respectively. So what does that mean? If we have K's that are different from one another, the solution to the natural frequencies will be much, much more different. So in a sense, our system is very sensitive to the properties of the mass and stiffness. So all right, let's open up our impedance matrix. So this is what it actually looks like per element. What we're going to do is we're going to take the determinant of this and equate it to zero. So this one is simple. It's just Kramer's rule. The prime diagonal, take the products, then subtract that with the products of the minor diagonal. And eventually, you will arrive at a quadratic equation. The solution to those quadratic equations will be the system's natural frequency. And what are those? So those are this. So this first natural frequency, square root of k over m, and then this one, square root of 3 times k over m. So is the numbering important? Yes, actually, the numbering is quite important, or rather, not the numbering, it's the order of the natural frequencies. So, all right, so we've solved for the natural frequencies. Now, if you still recall, we're going to need to solve for the associated mode shapes. So each natural frequency has an associated mode shape. And to go about that, we are going to substitute this natural frequency back into the equation. So this is what it looks like when it's back in. So there's our omega n squared. And what we're going to do is, okay, we're going to solve for this. We're going to simplify our impedance matrix. And we get this. This is now our entire matrix equation. Now, before you proceed, we're going to talk about the forms of x1 and x2 under this first natural frequency. What we have to understand is that since we're exposing our system to this natural frequency, these two displacement functions actually vibrate to this natural frequency. It might seem kind of obvious at this point, but if you start solving for the responses, it will get very confusing very fast. So if you look here, we have our x1. Ooh, what is this? We now have a new denotation. This is a parenthesized superscript. So when you see something like this in ME 160 or in a vibration reference textbook, this usually denotes the mode shape number or the order of the natural frequency. So if you see x raised to parenthesized 1, that means this one is the associated displacement for the first natural frequency. So I have x1 raised to mode 1 and x2 for mode 1. It's kind of confusing when you try to verbalize it, but yeah, bear with me. So what is the implication of this? So since x1 and x2 are vibrating to omega n1, we can bring out the complex portion of the equation. So this one we can jettison. We can reject this and just focus on this part of the equation. So this one we equate to the zero vector, and regardless of which you pick, the first row or the second row, you will always end up with the following relationship. You will end up with x1, the amplitude of the first displacement, and the amplitude of the second displacement being equal. So what does this imply? If our x1 here moves 5 millimeters to the right, x2 will also move 5 millimeters to the right. They are synchronized in their motion. Now, here's the thing. We do not have initial conditions that are needed to fully solve for the response. But we don't need the full response. We just need to look at the relationship of the amplitudes. So now, okay. So the displacement vector for the first natural frequency would be something like this. So keep in mind, parenthesized superscript 1 means it is for mode 1. So this is the displacement vector for mode 1. This is x1 and x2 for mode 1. And because x1 and x2 are kind of equal, you can kind of substitute x1 to the amplitude x2. So you can factor out x here and then just leave the multipliers. So it's plus 1 plus 1. Now, what is this plus 1 plus 1 vector? This is our first mode. So for the first natural frequency, this is the associated mode shape. All right. So now let's move on to the second natural frequency. If we do this, the same process, we will actually end up with a very different result. Now, for this second natural frequency, what you notice here is that our x1 and x2 are now denotated with a parenthesized 2. So if you see parenthesis 2 as the superscript, that means they are linked to the second natural frequency. Okay, so both of these are vibrating to omega n2 currently. So if you do the same process, you will end up with this relationship of x1 and x2. So now, when x1 moves 5 millimeters to the right, x2 will move in the same magnitude but in the opposite direction. So what you'll have is this kind of relationship between x1 and x2. And this is your second mode shape. So this is the shape of your vibrational pattern when it is exposed to the second natural frequency. All right. So again, when we have our first mode triggered by the first natural frequency causes the system to move in sync. So x1 and x2 move in sync, and more importantly, the graphs, the displacements, they overlap. Now, if we trigger our system using the second natural frequency, x1 and x2 will actually move opposing each other. So the displacement graph will look something like this. So if x1 is up, x2 is down. x1 is down, x2 is up. And what you notice here is that the second mode is actually producing a tighter displacement. And that is because omega n2 is larger than omega n1. So the order is important. This is a summary of the possible shapes of a 2 degrees of freedom system. So if you see mode 1 here, it kind of mimics a single degree of freedom system. Now mode 2 is something that a single degree of freedom system cannot do. So mode 1 imitates an SDOF system. Mode 2 is something that the second degree of freedom system can do, but the no the 2 degrees of freedom system can do, but the single degree of freedom system cannot. So if you extend that to the 3 degrees of freedom system, you get the same pattern. So the mode 1 of a 3 DOF system imitates a single DOF system. Mode 2 of a 3 DOF system kind of imitates this one, the mode 2 of a second degree of freedom system. And then mode 3 is something that neither the single nor the 2 degrees of freedom system can do. And oftentimes, again, so the actual response of the system will just be sort of a sum of all of its modes. So if it's 2 degrees of freedom, it will be the sum of the response under mode 1 and then the response of under mode 2. That sort of changes depending on the disturbance. So the actual solving of the 2 degrees of freedom free response is actually quite complicated. The extended form of this is in your module, but that is not our focus for chapter 6. However, here are some things that you have to keep in mind. So again, the two responses to watch out for are x1 and x2. And both x1 and x2 are superimposed or rather superpositioned between their two modes. So there's an illustration of that. So x1 of t, so that's mass 1, is equal to the superposition or the sum of its responses in mode 1 and mode 2. That is true for x2 as well. So this can get very confusing very fast, and we do need initial conditions in order to solve for the responses to these disturbances. So like for example, this is one kind of body here. We have an oh, this is not an asymmetrical system. This is a symmetrical system. Oh wait, maybe it is asymmetrical in the module, but yeah. This is our system and these are the initial conditions. So we only have one non-zero initial condition. We have a flick, an initial velocity on mass 1. So okay, knowing what we know about 2 degrees of freedom systems, if I flick mass 1 with this initial velocity, will mass 2 move? So that is an interesting question. Because in chapter 1, we mentioned that the numbers of degrees of freedom depend on how many bodies can move independently. So does that mean if I flick mass 1, mass 2 will not move? Does that mean that? So if we get the response of our system, we find out that even though we only flicked mass 1, so that is the green line here, mass 2 will also be triggered to move. So that is interesting. Why does mass 2 move? That is because mass 1 is linked to mass 2 through spring 2. So when mass 1 moves, it transfers motion from itself through spring 2 and into mass 2. So the only way to stop the movement of mass 2 is to just clamp this down. So if you clamp this down, the only thing that moves is this one. So it becomes reduced to a single degree of freedom behavior. But if you free up mass 2, it is free to be influenced by initial conditions or disturbances that are coming from its other sister masses. So if mass 1 is flicked, eventually mass 2 starts to move. And what you see here in this entire graph is that sometimes it can be as chaotic as this. Sometimes there is no discernible pattern, although if you see here, there seems to be some mirroring if you look at it intensely enough. There is some sign of mirroring, but otherwise it kind of looks quite chaotic. Now, when it comes to real systems, the bodies that we encounter there are not fully rigid. So when they're not fully rigid, a lot of the regions of the body are kind of free to move on their own, and that results in an infinite number of natural frequencies. And because you have an infinite natural frequency count, you have an infinite number of modes. However, because the natural frequencies get tighter and tighter, they get larger and larger, the amplitudes that they can produce are quite small. So in essence, like if you go beyond mode 6, mode 7, mode 8, maybe the amplitudes will not even show up in your macroscopic view. Like perhaps the only thing that you'll be able to discern would be, like for example, if you have this beam here, if you expose it to a numerous natural frequencies, perhaps the only thing that you can discern would be modes 1 through 4. It's possible. So if the influence of mode 5 is really weak, maybe you can just reject it from the analysis. So actually in Fusion 360, there is a mode shape sensor, or rather mode shape simulation. Um, you can find it in Fusion 360 or Autodesk Fusion. It will quickly give you which frequencies trigger the most amount of vibration in your system or in your assembly. And that kind of helps you determine how to strengthen your parts against dynamic loading. So that kind of concept is actually important when it comes to three-dimensional complex assemblies, like this altimeter attachment to the satellite that we've seen before. So we have several different modes. Again, these are exaggerated, so they won't actually shake like this, except maybe mode 1 and 2. Mode 1 and 2, maybe it's likely to be that bad. But what you have to look out for, okay, so under mode 1 and mode 2, which parts are experiencing the most amount of stress? So depending on that, you can actually trace which one is being stressed out the most. And you can determine what kind of material properties will be required to resist the shaking under mode 1 and mode 2. So that will be your process when it comes to strengthening parts for exposures to their natural frequencies. Now, all right. So, what are mode shapes then? So, the mode shapes are associated with the natural frequency. So, in mathematical terms, the natural frequency is what we call the eigenvalues of the system. So, these are the eigenvalues of the system. And the mode shapes, these are the eigenvectors of the system. So, these two, the natural frequency and the mode shape, are inherent characteristics of a two degree of freedom system. So if you recall, the eigenvector of a matrix are those vectors that do not change in orientation if you transform it using a particular linear transformation. So for example, okay, so if I plot this particular matrix and use it to transform my unit grid universe, these eigenvectors will not change in their orientation. So that is the mode shape. And the warp, the level of warp that those orientations experience will be the natural frequencies. So again, the important point here is that the natural frequency as well as the mode shapes are actually inherent to a vibrational system. So this is inherent regardless if whether it's a single degree of freedom system, a 3 degree of freedom system, or a multiple degree of freedom system. They will always have a natural frequency and an associated mode shape. So, sir, what about single degree of freedom systems? What about SDOFs? Do they have their own mode shape? Yes, they do have a mode shape, but it's only one. So it's kind of not useful to just it's kind of not useful to label it as mode shape 1 because it is the only mode shape that exists for a single degree of freedom system. So mode shapes kind of become more relevant because if you have two or more natural frequencies, you have to distinguish between the mode shapes. So yeah. Now let's look at other two degrees of freedom systems because so far we've only used symmetrical types of systems. So when I mean symmetrical, meaning you can kind of divide the system in half and you kind of get a reflection of that. So what we're going to do now is we're going to take this spring, this rightmost spring, away from the system. So the body will now look like this. So it is only tethered to this wall, and mass 1 and mass 2 are still free to move, but they're only tethered by these two springs. Of course, you have mode 1, which is where these two masses they move in sync, and in mode 2, these masses will move in opposition to one another. So what would be the natural frequencies of these systems? So we will not solve it, but you can check these are the natural frequencies of our system. So they are much different compared to this. We just took away one spring and it made all the difference. All right, so the natural frequencies changed. How do the mode shapes themselves change? They now look like this. So what you see here is that mode 1, they still have the same sign, but one of them is no longer in step or 1:1 with the other. So if the x1 here moves 1 millimeter to the right, M2 will move 1.61 millimeters to the right in response. Same thing with mode 2. They are still in opposing signs. So they will oppose one another, but the degree of amplitude that you have for M1 and M2 are vastly different. So if you plot the response, it kind of looks like this. So the mode 1 of an asymmetric 2 degree of freedom system will have this profile in mode 1. So the x1 and x2 responses no longer perfectly overlap. And that is true for mode 2 as well. So, all right. Now, if you want to examine, okay, so how does that affect the response of your system? So, okay, we're going to subject it to the same initial conditions, but we already took away this spring here. What is the response of our system? So just like before, mass 1 is flicked, but mass 2 will be eventually triggered to move through spring 2. However, you notice here, the graph kind of looks different. It looks a lot more different. So let's see. This is our symmetrical setup and this is our asymmetrical setup. So they kind of look different. Although it's kind of too hard to see, but yeah, they are different. And that is the effect of just changing one bit of the system. So in a sense, every 2 degree of freedom system is kind of unique. So their impedance matrix are unique to one another. So you have to reset. You have to go back and solve for the natural frequencies, the mode shapes over and over again if the properties or the involved elements change. So now let's look at harmonic excitation or forced response. All right, so it feels like we're speed running, right? So here it gets a little easier. This is our 2 degree of freedom setup. It's symmetrical. This is our equation of motion in matrix form. And this is our characteristic equation. Now, the thing here is that we're not really interested in x1 and x2. Rather, we are interested in the steady state amplitudes that are being induced by this external force. So to get that, we don't really have to look at the modes themselves, although the natural frequencies will show up later. So to get x1 here, we just have to get the inverse of this impedance matrix and multiply it to our force vector. So our force vector here would be F naught, the forcing amplitude of F1 here. And then for the second mass, you don't see any forcing. So this is essentially F naught 0. F naught 0. So this is what it looks like actually. So your X here, this is our X. It's vibrating to a forcing frequency. And this is our inverse impedance matrix. And this is our forcing vectors. Just F1, 0. So how do we get the inverse? Again, we essentially swap the primary diagonals, then multiply then change the sign of the minor diagonals, then divide it by the determinant. So it kind of looks like this. All right, hold on. Okay, sorry about that. So yeah, this is now your oh, I forgot to remove the raised inverse sign. So yeah, this is your inverse solution. So eventually, you will actually end up with an expression for x1 and x2. So I'll leave that to you to look into the module and see what the steps are. But the expressions for steady state x1 and steady state x2 are the following. So this is steady state x1 for this mass 1, and this is x2 for x2. So what you notice here is that x1 and x2 share the same denominator. And what are those denominators? So, oh, it's this one, and then it's this one. And something's familiar about them. If you equate this to 0, either of them, you'll actually get the natural frequencies for this system. So that's square root of k over m, you'll get it through here. And you have your square root of 3 times k over m, you have it here. So the denominators are the natural frequencies. What else do we notice? For x2, yeah, it's k times f1. Okay, no big deal. However, if you look at x1, there is a difference term. So you have 2k minus m omega squared. The interesting implication of this is that there will be a frequency, a forcing frequency that can trigger a zero amplitude. So that is amazing, actually. So now we have two notions for our steady state amplitudes. So first and foremost, on our denominator, we have our natural frequencies. If omega hits those natural frequencies, what happens to the amplitudes? They grow to infinity. And for x1 uniquely, at least for this case, we have a condition for a zero amplitude. Now again, for x1 and omega, we do have normalization options. So again, if you recall, the normalized x is actually magnification m. The normalized omega is actually r, the frequency ratio. Just what happens for this case, okay, so since we have two natural frequencies now, we have two frequency ratios. We have R1, which is omega, the forcing over the first natural frequency, and we have R2, which is the forcing over the second natural frequency. And you arrive eventually at these expressions of M1 and M2. So if we graph that, it kind of looks like this. Okay, so you have your M1, this is your X1 essentially normalized, and then this is your M2, which is normalized X2. It kind of looks weird, but if we take the absolute of this entire function, we get this. So we can actually spot something interesting. So first and foremost, where are the natural frequencies? Here they are. These are the natural frequencies of your system. So this is the first one, and then this is the second. Next, where is the zero amplitude of x1? So x1 is now m1 here. It's actually here. Sir, what are the implications of this? So this has strong implications for vibrational absorbers or tune mass dampers, but that will be for a future lecture. And for now, thank you so much. And I hope you have a great day.